So this is the last talk of this today. Miriam Gordin will be talking about vector value concentration of the symmetric group.
Okay, so thank you for the introduction and for the wonderful school. And I'm especially grateful to Alexandros because he kind of introduced what I'll be talking about very well in his mini course. So as he kind of stated as the goal of his mini course, the main aim will be to prove functional inequalities for functions that take values, in this case in a Banach space. And one thing that a property that we want these inequalities to have is that they have dimensional constants in a way that we get some embedding results. So for the case of the inequalities I'll talk about, we'll get some nonembeddability of certain discrete metric spaces into Banach spaces. So that will really be the goal. And what I'll talk about is kind of some results we have for inequalities where you make basically no assumptions on the target Banach space, and we'll see what kinds of inequalities we have. So there are very few kind of results known in this generality, and the classical theorems date back to Pisier. So I'll first state his result on Gaussian space, because there was also a question at some point of like, oh, why are we working on all these discrete spaces, and is it also interesting to consider continuous time or continuous spaces? So a very classical theorem of Pisier from 1985 says that if you have a function going from Rn to some Banach space X, again with no assumptions on X, which is locally Lipschitz, and you take G and G prime to be standard normals distributed on Rn. Then for P between 1 and infinity, he proved the following inequality. So the expectation of F applied to G, centered at its mean, is bounded by some constant times the expectation of these independent Gaussian coordinates multiplied by the gradient of F evaluated at P. So the proof of this inequality relied very heavily on special properties of the Gaussian distribution, namely rotational invariance. So the method for proving this inequality doesn't really translate to other spaces, but as you can see, here we have a dimension-free constant, and this means that this inequality really kind of captures the dimensionality in the correct way. And so in the same paper, he proved essentially an exactly analogous inequality, but on the hypercube, and there we'll start to see right away why we have some dimensionality issues appearing when we try to take the types of results that work on continuous spaces and just write down their analogs on discrete ones. So,
by the way, on the right, should it be the jth partial instead of the gradient?
Yes. Thank you. So a theorem from the same paper will be directly analogous to this. So now we have some function going from a hypercube to a Banach space X, and we need to define some notion of derivative that will be the analog of the gradient. So I think we've already seen this before. That will just take F minus F evaluated at the point on the Hamming cube with the sign flipped at the coordinate I or J in this case. So now if we take epsilon and epsilon prime to be independent, uniformly distributed on the hypercube, he obtains the analogous inequality. it turns out that the dimensional constant is of order log n, so growing with dimension, and in 1993, Pellegrin showed, by finding a specific example, that this is sharp. So we cannot get better than log n in this inequality, and this was exactly the obstruction to the fact that Alexandros mentioned that n-flow and Rademacher type are equivalent. So if one were to have just a constant here, not depending on n, that would immediately imply that. But since we know that this log n is sharp, that was kind of the reason why that implication between n-flow and Rademacher type remained open. And then, so in 2020, in a very nice work of Sasha, Ramon, and Pata, they proved the equivalence between n-flow and Rademacher type, and that was done through identifying a different sort of inequality, where they observed that rather by kind of operating analogously to the Gaussian inequality, where we have the same distribution of random coefficients here as the original measure that we're studying, that if one instead has some different random coefficients here, that one actually obtains the equivalence between n-flow and Rademacher type and the dimension-free constant in the functional inequality. So let me write down the result that they have, because our work on the symmetric group is kind of extending the methods that they use to prove that. So see, I'll just write it here. So theorem So we'll work in the same setting, but we have a function on the hypercube going into a general Banach space, and between 1 and infinity, we found the quantity expectation of f. So the norm of expectation of f centered by its mean is bounded by the integral from 0 to infinity of the expectation, the sum over the coordinates of the hypercube, delta jt, which will be our new random coefficients, times bjf epsilon as before. I think I'm missing a constant over 2, but anyways, it's not very important. Okay, so this is the inequality, which exactly if you just plug in the definitions of n-flow and Rademacher type, you'll get the equivalence. So you really have this connection between functional inequalities with dimension-free constants and notions of equivalence of type. So here I haven't defined what these delta jt's are, and in the case of the hypercube, they're an independent vector of random variables, which are essentially rescaled Rademachers. So somehow we're integrating over t, a parameter from 0 to infinity, and these delta jt's are renormalized Rademachers whose values and distribution depend on this parameter t. And exactly by introducing these variables, they were able to prove a dimension-free constant. And in the case of the hypercube, I won't write down their distribution, but you can write down them exactly, and you can operate with them and very easily and kind of get very precise bounds. So yeah, if you want the details of it, you can look at the paper. But where this is coming from is using a Markov semigroup interpolation argument, which is a very classical method in proving concentration inequalities. And the main idea is that one can interpolate between the two objects appearing on the left-hand side of this inequality, where we have this f evaluated at our random string of -1s and 1s minus its expectation, and by using the Markov heat semigroup to interpolate between these two objects, we obtain these random coefficients. coefficients. So, yeah, and as I said verbally, yeah, the corollary of this result is that Handel and Rademacher correspond. So now I'll talk a bit about how we, does anyone have any questions about this? So I'll talk a bit of our work with Ramon, where we want to extend this idea of using semigroup interpolation to prove these inequalities with really a very general target space and kind of the difficulties that we encounter. And the main thing that we wanted to go beyond is that in the case of the hypercube, first, because it's kind of you're considering a measure that just takes value on 2 different points, you can operate with a lot of things directly, but more importantly, because you have a product structure, you have a lot of nice probabilistic independence properties. So notably, the fact that these random coefficients are independent across the coordinates j. And as soon as we try to extend this to a more general setting, we lose those properties, and so we have to do a lot more work in order to get nice functional inequalities. So I'll talk about that now. So now we're kind of moving away from the hypercube, which is supposed to be the topic of this school, but I'll hope to talk about some application on the hypercube at the end, so we'll circle back to it. So first I'll write down how one can generalize this sort of inequality just to any finite group setting. So I'll go over some preliminaries, and it'll also make it a bit more clear where the distribution of these delta JTs are coming from and how they're related to the Markov semigroup. So we'll take G to be a finite group with S a symmetric generating set. And we'll define the discrete derivative indexed by each of the generators of the group as the difference f evaluated at G minus f with the generator applied on the left. And then we can write down the Laplacian of this group, or equivalent, you consider the Cayley graph of the group as just minus the sum over these derivatives ds. And so we'll work with the heat semigroup induced by this generator. So more precisely, in order to operate it with it probabilistically, we can equivalently consider xt, the continuous time random walk on the group, which we'll define in the standard way that you have a Poisson clock ringing at some rate, and every time it rings, you choose a new generator uniformly at random and apply it to your walk, and so you continue rambling about your group. So we'll denote as mu the stationary measure of this walk, which will be the uniform measure on V. So I made a mistake with the order of the boards, but so we'll denote as PT xy the heat kernel of this random walk, which is just the probability that your random walk ends up at the point y in the group, given that you started at some point little x. So then the definition of these delta JTs, now we're indexing them by S, we can write it down as the following difference quotient. So delta ST is a random variable given by PT evaluated at x0 and xt minus PT at now initialized at S applied to x0, xt. Sorry, is this not visible from the back? So if you consider the discrete hypercube as a group and you go through the definitions, you'll get exactly the same thing. So these random coefficients are really coming from, you can think of them as discrete analogs of the gradient log of the Hughes kernel of the semigroup on whatever space you're working on. And kind of it will become clear that by understanding these random coefficients, we can control the right-hand side of this inequality. So what is the vector-valued concentration inequality that we get in this setting? So composition. So if now we have a function going from B to a general Banach space X, and again the same P before, we have that the expectation of F with respect to the uniform measure on the group is bounded by this integral from 0 to infinity of the expectation, the sum over the generators of our delta ST coefficients times ESF evaluated at x0. So here the expectation is taken with respect to the distribution of the random walk. So our delta ST is depending on xt and x0 in this definition, and then we're evaluating our function at x0, which is distributed according to mu. So we're taking the stationary walk. Okay, we can write down this inequality. It turns out you can do this on any discrete metric space. We're not using the group properties at all, but by itself, this is not very useful because what we have on the right-hand side is we have some, in general, dependent random coefficients multiplied by elements in a Banach space, and this is like every probabilist nightmare of dealing with first a sum of dependent things, and now they're taking values in a Banach space. So kind of the main challenge is how can we estimate the right-hand side? And we were able to do this in the specific case of the symmetric group, taking the generating set of all transpositions. So I'll write down now what we get. So make sure I'm not forgetting anything that I wanted to say. So now we'll take a function going from Sn, where as our generating set, we'll take the set of all transpositions ij with I ranging from 1 to n. And now, so our function is going to x, and we'll assume now that x has Rademacher type P. So, as was mentioned in the meeting course, the only possible values are 1 and 2. So if it has 1, we say it has trivial type, since that's satisfied by any Banach space. So I'm running out of space, so I'll write the result here. So in this case, we obtain the following, what we could call vector-valued Pisier, or Poincare inequality. That again, the expectation with respect to the uniform measure on the symmetric group of F centered is bounded up to some universal constants by log n over n to the 1 over p times the sum over our transpositions ij of the expectation with respect to mu of bij f p. So here, I mean, clearly there's still a dependence on n, but it's even better than what we call dimension-free, in that we have decay with n. And the corollary of this result is that we obtain nonembeddability of the symmetric group into Banach spaces of non-trivial type. Okay, maybe before I write that down, I'll just say verbally a few ideas of the proof. So as I said, the kind of most difficult challenge is to estimate the right-hand side. And kind of in the case of the hypercube or of a product group, we have independence of these deltas t's. So why were we able to prove this result in this very specific choice of the symmetric group with this generating set? So first we use the fact that since this generating set is a conjugacy class of the symmetric group, we can derive an exchangeability for these random coefficients. So we don't have independence, but we have exchangeability, which is only a bit worse in some sense. And what that allows us to do is to perform a symmetrization argument on the sum, which allows us to introduce independent Rademacher signs here and allows us to apply Rademacher type, since if you recall the definition, it really has to do with how the norm of a sum of elements in a Banach space scales when you multiply them by uniform random signs. And then the second step is that we need to obtain estimates on these, the moments of these deltas t's for exponents between 1 and 2. Because in principle, like one of the issues with this inequality is that you don't even know a priori if this right-hand side, if the integral converges at all. So we somehow need to be able to control the moments of these coefficients in a way that we both obtain a good dependence on dimension and that the dependence in t is such that this integral converges. So that's kind of everything that's under the hood of this result, and something that I think is nice about the proof is that we end up using a lot of probabilistic methods, even though the question is kind of starting from something in really the analysis of Banach spaces, one could say. So maybe I'll just say, because it'll come up later in the application, that the way we obtain the estimates on the expectation of these, the moments of these delta t's for p between 1 and 2. So if you recall from the definition, these random variables are coming from some difference of the heat kernel of the random walk. So kind of the nice thing about this method is that we can separate what's going on with Rademacher type and the analysis on the Banach space, and then what is going on with each step of the random walk on the group. And we end up using two different sets of techniques in order to control these moments. So before the mixing time of this random walk, which by Diaconis and Shoshani is around 1/2, or very precisely at 1/2 n log n, for the regime before mixing, we can use the notion of Emery curvature, which is an analog of Ricci curvature that can be made sense of on graphs in order to control these moments. And then after mixing, we use precisely mixing time estimates. So we can kind of bound the numerator and the denominator of this expression using the total variation and separation distance mixing times, so classical results from the 80s of Diakonos and Shoshihani and others, in order to get sufficient decay to evaluate this integral. Are there any questions?
So you use Pisier for the curvature. What is curved to you?
What is curvature?
No, what is curved? You use this for, I mean,
So
you need something with a curve to use Pisier.
yeah, so this notion of curvature makes sense for any Markov semigroup. So if you are working on continuous space, like if you have a random walk on a manifold, then it corresponds exactly to Ricci curvature. But somehow you can make sense of the notion even on a graph. So if you consider a graph geometrically, because it kind of goes through the machinery of gamma calculus and Markov semigroups, you have a notion of a gradient, the gamma operator that's defined, and so you can use this notion of curvature on graphs. And what it's doing and why it is in spirit like curvature on a manifold is that it's really capturing the local structure of the graph. So for example, trees or other graphs that are like hyperbolic in spirit will have negative curvature. Other graphs like the complete graph or the Cayley graph of the symmetric group with all transpositions will have positive curvature, and then the lattice will have zero curvature, so it kind of captures the flatness. So yeah, and I think this is a really nice idea, and like in the ideal, we would just be able to capture like everything about how these delta JTs behave based on the curvature, because that's something that you can compute quite easily, like it's a local property of the graph. And then one would hope that it kind of contains all the information you need. It turns out that that's not the case in this theorem, but yeah, I'll come back to the idea of curvature in the application on the hypercube. Are there any other questions while I'm erasing the board?
So this factoring depending on angle type?
No, so in order to match with the conjectured bounds, this log n factor would not be here. So we believe that it's just a technical artifact of this group and have some ideas of how it could be removed. But up to that log n factor, we've really obtained the optimal dependence on the dimension. So for example, Alexandros was mentioning the result of Cote-Noir, which can be applied to the symmetric group. And there, say for embedding into Hilbert space, you get, okay, what I was going to write down just now is which distortion you get for an embedding. So from this result, we recover up to this factor of log n, the dimensional dependence that was known for a more restricted class of Banach spaces. So yeah, maybe I'll skip recalling the notion of bi-Lipschitz embedding unless someone wants me to repeat the definition. Okay. So the corollary of this theorem, which is the consequence for nonembeddability, is that for any function going from the symmetric group with this generating set Qx. So, where x is a Rademacher type P, then we have that the distortion of f is bounded from below up to universal constants by n to the 1 minus 1 over p times 1 minus log n to the 1 over p. So again, this corollary comes just from applying the notion of, like, assuming that f is a bi-Lipschitz embedding and applying, plugging it into that inequality and kind of considering like the diameter of the space, etc. And you immediately get this lower bound on the distortion. So if this log n factor were not here, then this would recover the dimensional dependence that was already known for a more restricted class of Banach spaces. So if there are no questions about that, then I'll finish by talking about an application to the K-slice of the hypercube. So let me first define what that is. So I'll denote as h and k the K-slice of the hypercube, which will be, and now again we're switching from the -1,1 hypercube to the 0,1 hypercube, so it'll be all strings of zeros and ones of length n. So all of x such that we have k1s and n minus k0s, but in any order. And we'll take the transposition metric on this set. So if you say your n is 5 and your k is 3, so we have 3 ones, then how can we move around the space on all of such strings? Well, if you just switch any 0 and 1, you are preserving this property. So it's very natural to consider the symmetric group with transpositions acting on this space. And so one could get a lower bound on the distortion going from the K-slice of the hypercube into a Banach space just by directly applying the theorem there. So you kind of consider all functions of the form that you first have a mapping from the symmetric group into the K-slice. So it's an injection where you just are kind of identifying all permutations up to some equivalence between k of the coordinates being marked 1 and the other n minus k being marked 0. But if you just do that directly, you won't pick up the optimal lower bound. So if you just go into the details of the proof and do a few small improvements, you can immediately get a distortion lower bound, which is that if we have f going from the K-slice of the hypercube to x of Rademacher type between 1 and 2, which is bi-Lipschitz with distortion d. Then we have that d is bounded from below up to universal constants by the minimum of k and n minus k, all to the power 1 minus 1. So the nice thing about this result is that you see that we've lost the pesky log that was an issue on the symmetric group, and that's exactly because this space has qualitatively a different curvature in the sense of a Crée-Marie than the symmetric group. So the symmetric group has constant curvature 2, which means that if we only use the estimates on these delta STs coming from curvature, we'll still have the right-hand side converging, so we can evaluate the integral, but we won't get the optimal, or not even optimal, but we won't get the dependence on the dimension that qualitatively will tell us that we have nonembeddability for Banach spaces of non-trivial type. So there we really, in the case of the symmetric group, need to combine the Crée-Marie curvature with mixing time estimates in order to obtain the final bound. But it turns out that on the K-slice, our curvature is even more positive, so it scales like n. And so by using that information in the proof, we're able to obtain this bound, which I think should match with the estimate of Cote-Noor for K length. I guess in that case, metric spaces. So let's see how much time I have left. Okay. I somehow spoke much faster than I anticipated. But okay, so are there any questions? Yeah.
So because the case size has like omega n curvature, then you can just use the Crée-Marie the whole way, and you don't need to change them sometimes. That's how it works.
Yeah. Yeah. So maybe in the last minutes I'll comment on.
Okay.
Oh, yeah.
So another question, the remark, because you said you use the transposition metric, but this is up to a factor 2, the same as the L1 metric, right? Because if you have two strings of length k which differ on j spots, then j has necessarily to be even, right? Because they have the same numbers. And then the L1 distance is j, but the transposition distance is j over 2, because you just have to pairwise swap. So it's the same metric. So you find a much smaller subset of the hypercube, which is the slice, which has exactly the same distortion. So it improves also the distortion bounds that followed from the work of Ivanisvili, Van Handel, Volberg.
Yeah, so I think that's a question that I find very interesting, that kind of, if we have estimates on curvature, then we immediately get certain gradient estimates and other estimates on these delta STs, but somehow curvature is a very local notion, so it's interesting to consider like whether there are other examples of the symmetric group acting on some space where maybe the symmetric group has positive curvature but not as positive as we need, but maybe with some modification or considering certain like interesting spaces that the symmetric group acts on, or even a hypercube potentially acting on some space. One could find spaces with good curvature that allow us to get these very nice estimates.
So you can find something between the K-slice and the symmetric group, which is multi-slice. So now it's not 0, 1 to the n, it's like some finite alphabet, and you fix the histogram. If it's 1 up to n and it's 1, 1, 1, it's the symmetric group, and this is your case, and you can get everything in the middle.
That would be interesting.
What will you hope to get from that?
I mean, in general, what I really wanted to verify is that in general you want somehow the smallest set that has the curvature that you can use to prove.
But yeah, somehow with curvature, it's like, I think this condition could be used in different ways. That, for example, here you consider like one step of the random walk on the graph, but you could in principle consider like the curvature with respect to 2 sets. So I think there are a lot of different things that one can play with in order to potentially carry over these types of arguments to more spaces. And I think really what kind of is the main idea, that we can use a lot of probabilistic techniques coming from a completely different area in order to get estimates to obtain these functional inequalities. So yeah, maybe the last thing I would comment is that there's a different type of distortion, average distortion, and these theorems also give us lower bounds on the average distortion. And in some sense, we could think that in obtaining these lower bounds on bi-Lipschitz distortions, that's really a very crude application of the theorem, because on the right-hand side, we have this expectation over mu of dijf, so the difference of the function across two neighboring nodes in a graph, and then we're just bounding that expectation deterministically by the Lipschitz constant. But in principle, the inequality is saying something more general, that one has the statement not just in the worst case, but also on average. So we say that a function from some metric space M, Banach space X, has average distortion D if X is the Lipschitz. Okay, here I should say that as soon as we have average, we need to fix what measure we're considering. So average distortion with respect to a measure mu, and the expectation with respect to mu of So the expectation of the function at one mu distributed random variable minus the function valued at an independent copy of that variable is lower bounded by that average distance in the metric space. And I won't write it down, but essentially, from these inequalities, we get. Yeah, so, I mean, as before, the scaling doesn't matter too much because we're in. So here we have the upper bound that D is Lipschitz, but the lower bound is average instead of a worst case lower bound.
So would it be a different definition if you started with what's the opposite of non-contracting and asked that the expectation would be smaller than D times the expectation? Would these two definitions be different?
I don't know, do you know?
Completely,
Yeah.
Because here you see, even by looking at the inequality, you tend on the right-hand side to control edges, but on the left, you really have the variance, so two independent points. So I think that's
Yeah, in principle, I mean, this is the definition that exists in the literature that has been studied and also been like carried over into like infinite dimensional metric spaces. So somehow, yeah, at least for this definition of average distortion, we obtain the same dimensional lower bounds also on the average distortion, not just on the worst case by Lipschitz distortion. And this also opens up kind of other applications of vector valued concentration inequalities, where now instead of considering uniform measures on these spaces, we can also consider other measures. So yeah, I have also some results on the bias product measure on the hypercube, which improve the original result for the uniform measure on the hypercube, where I can obtain optimal lower bounds on the average distortion in terms of both the bias parameter and the dimension. So yeah, that's kind of another interesting notion of distortion that one can consider. So I think I'll finish there.